So yeah, I was saying that yeah, just Michael is very passionate about open science and reproducibility of our data, of course. And today he's going to give us a tutorial on dMRIprep. This is an extension of the fMRIprep approach and principle to diffusion MRI. So as I already told you, he already shared the link to the Jupyter notebook in the chat. And Michael, the floor is yours.
Thanks for the introduction, and I'm happy to be here. So if you attended Oscar's talk on Tuesday, where he introduced the dMRIprep tools, you can think of this tutorial as part 2. So I posted a link earlier in the chat. You can access the talk materials at www.dmripreps.org/dmripreps-book. And so with this tutorial, I'll go over how you, as a potential new contributor, can engage with the dMRIprep tools, dMRIprep in particular. We'd really like to continue building up the community around these tools. So I'll start by giving an overview of dMRIprep, and I'll introduce you to some basic diffusion MRI concepts. Then I'll go over how dMRIprep is structured as a project. We'll review a long-standing new feature in the software that we've been wanting to implement and do a code along the way, so you get introduced to some of the different components involved in dMRIprep. And finally, we'll push the changes to GitHub. And yeah. So this talk is rendered in what's called a Jupyter notebook. It's a series of IPython notebooks that combine code and ideas into one solid format. So I'm going to click on the next chapter about dMRIprep. And over here, in each of these chapters, you should see a rocket ship with a binder logo on the side. So if you click that, I'm just going to open it in a new tab. This will take us to a binder link. So it'll create an interactive Python notebook. And I'm just going to execute, sorry. Let me just drag my screen over. How does that look? So yeah, here we have a Jupyter notebook, and this will allow us to kind of execute the code simultaneously. So dMRIprep evolved out of the success of fMRIprep. Traditionally in neuroimaging, researchers create these ad hoc preprocessing workflows for each data set, and sometimes there can be differences in the way sequences are acquired or different pre-processing steps along the way. All of these complexities make it a little bit hard to create these pipelines. So with fMRIprep and now dMRIprep, we're trying to create a reproducible pipeline that'll take your inputs in, take your data set in as a BIDS data set and robustly figure out the best strategy and workflows. So dMRIprep arose from an earlier work by Ariel Rockham, Anisha Keshavan, and Adam Ritchie-Halford. So I joined later on when I was trying to revamp my own lab's diffusion imaging pipelines. And one thing that I learned about this is as a contributor to something that's open source, you end up learning a lot of new skills, and you can accomplish something greater than what you're able to do alone. So in terms of the pre-processing steps involved in dMRIprep, they were kind of informed by this 2019 ISMRM talk on the state of diffusion imaging pre-processing. So this talk was given by Jelle Verart, and he pulled the developers of some major diffusion software packages to see whether there was any consensus in the field. And the results were pretty encouraging. So it showed us that there is, it showed us that there is consensus in a few different pre-processing steps. There are some steps where kind of the acquisitions need to be synchronized with the pre-processing. So for example, if you were to do some distortion correction for your diffusion pre-processing, the best practice is to use phase encoding field maps, so like a particular acquisition. But there are also other steps that they, I guess, need more work in determining whether they're actually useful in the final result. So there's a lot more work that needs to be done on, can we agree on certain algorithms that we can use to perform these processing steps? And can we agree on an ordering in which all of these steps can be executed? And I'll talk about how maybe I'll actually share my whole screen. I think that'll make it easier. All right, there we go. So next I'll talk about how dMRIprep enables us to answer all these questions. So dMRIprep is part of the NIPREP's organization. And all of the NIPREP's tools have some common philosophies. So we want to create pipelines that are robust and run on a diverse set of data sets. They're all easy to use, so they follow a BidZap execution model. So you have your standard pipeline run, and then a few arguments that are mandatory. So your bids, take in your bids data set, outputs to a specific folder, and an analysis level, so participant. They're reproducible, so they involve these QC reports. They're containerized in these Docker or Singularity containers that Martina mentioned earlier today. And they include boilerplate language for things like citations. And all of this also has a glass box architecture. So we can find all the code on GitHub. And a lot of the discussion is done through GitHub issues. So you can see how different parts of the pipeline came to be. And so here I have a hierarchy of the NIPREP's tools. So you can think of this as kind of a pyramid where at the top you have these end user applications. So dMRIprep being the latest one, fMRIprep and for functional data, and smRIprep for anatomical data. Within dMRIprep, there's also a lot of software infrastructure behind this. So you have NIPipe, which is a workflow engine. It allows you to interact with various software packages like FSL and AFNI, all within a uniform Python interface, and chain them together into a workflow. So in NIPipe, the interfaces are doing the work, and the workflows are what's chaining them together. So I'll show you an example of an existing, how do I change to? Okay, sorry. I'll show you an example of an existing workflow in dMRIprep. So let me just make that text bigger. So within this workflow, this one, what it's doing is it's skull stripping your diffusion image. So each workflow takes in an input, a set of inputs, so your diffusion image itself, and a set of outputs. So this would be kind of your skull stripped diffusion image. And they're connected by nodes, and each node has a certain interface. And interfaces are typically They can be Python functions, they can be functions from other software packages. So here you have FSL, possibly Bet was involved in this, or masking from AFNI. And yeah, so the interfaces are what's doing all of the work here. And as you go on, you have Nye workflows. So you could think of this as NiPipe supercharged. It has 3 times the number of logos. Nye workflows is involved in creating the visualization reports for fMRIprep and dMRIprep. And it also has common workflows that's shared among the different preps tools. And also, so learning some of these lower level software infrastructure tools are really important for being able to contribute to dMRIprep. I've linked a few, I have a few, sorry. I have a few links at the bottom of this page. To some tutorials that you can use. So yeah, next we created a roadmap for dMRIprep's development. And so here is kind of like our idealized roadmap and some of the things that we have on the go. So you can think of each of these components as an individual workflow. We can chain them together in different combinations, and that will help us see how the ordering of steps influence the ultimate result. And you can, with these different workflows, you can plug and play, so you can easily compare different algorithms. So before I get to the project structure, I'm going to go into a bit of an intro to Diffusion Mri. So with MRI, the type of sequence that you use has certain effects on the underlying tissue contrast. So in the case of T1 and T2 images, you can differentiate gray and white matter really clearly. I'll show you what happens with diffusion imaging. So this is an example of a Jupyter notebook. So you have your markdown text as well as code all in one place. And we can also run these different cells by either clicking the play button here or by typing Shift-Enter into your keyboard. So here I'm just loading in a diffusion image file, a BVEC file, and a BVAL file from a data set that we've added. And I'm loading in some packages from NiLearn so we can just plot the image itself. And for the sake of time, I'm only going to plot the first 10 images just to show you what that looks like. So I've indexed the diffusion image for the first 10 slices. I'm going to display the axial slice, and I'm just going to show you 3 different views. So here's what our image looks like. So we have, I guess, 10 different volumes plotted. And our first 5 volumes look pretty similar. I guess you can say they almost look like a T2 image. But our next 5 volumes look very different. So what this is showing is, so for our first volumes, we don't apply any magnetic field gradient. But then in our next 5, we apply a magnetic field gradient in different orientations. And each orientation captures the preference of water molecules diffusing in that direction. So how this looks is it shows as signal loss. So here you can see it looks like the gradient that we've applied is going in this way, and you can see these tracks really clearly. So we try to get as many different directions as we can within kind of like a set time limit, so the scan doesn't go too long, and we capture how the water molecules are diffusing. So next, I'll talk about the bvec and bval file. Those are two important files for diffusion imaging. So the b value file corresponds to the amplitude. I guess it corresponds to a couple of different things. So the amplitude of the magnetic gradient that we're applying, the time that we're applying that ingredient, and the distance between subsequent ingredients. So when you have, when you increase all of these things, you create a higher bval. And our bvec corresponds to the orientation that those gradients are applied in. So if you've ever converted your data from DICOM to NIFTY, you might be familiar with seeing these in FSL format. So I'm just gonna use cat to display these files. So you'll see that the bval is a single row separated by spaces, and our first 5 values are 0. So that's why over here we call these B0s. So these images are kind of used as reference scans, and all of the rest of the data are 1000. So this corresponds to a B value of 1000. You'll also see when we look at our bvecs, there was no gradient orientation applied for the first 5 volumes, but that changes. So for a bvec file, it's 3 different rows. One corresponds to the X component of the orientation, one corresponds to the Y component, and one corresponds to the Z component. So for each volume, you have a vector of 3 coordinates, so an X, Y, Z, and it will go towards a certain spot in space. So I'm going to use DiPy, which is a Python package specifically made for diffusion imaging. And I'm going to import the read_bvals bvecs function from DiPy. And this will just allow us to read these files into Python. And it reads it into a format called a NumPy array. So this is what that looks like. So our bvals are here. And you'll notice for our bvecs, it transposes them. So now our X component is in the first column, our Y component is on the second column, and our Z component is on the third column. And the next thing that I'm going to do is I'm going to plot what this bvec looks like. So I'm going to use the pyplot package from matplotlib. And I'm going to create a scatter plot with each of these values. And so you can see that overall it samples a kind of like a sphere. And you have, depending on the bvecs, you have different kind of sampling schemes, the way it samples your data. In dMRIprep, what we've built is something called the diffusion gradient table. So this is a class that does a lot of the heavy lifting. So I'm going to import that. And next, so in Python, if you want to find out more about a specific function, you can type out the function name and use this question mark. So that's what I did here. And this shows us all of the inputs that this class expects. So some of the standard arguments are it takes in your bval, your bvec, and diffusion imaging file. And we can do a couple things with this class. So I'm just gonna import it and assign it to the G tab variable. And I'm going to create a new cell using this plus icon. And I'll show you the different things that we can do with the G tab class. So one thing that I can do is I can output the bvex by using this ._bvex property. I can also output the bvals. We can combine them together, I think, using the .gradient. So here we have 4 columns. The first is the X component, second is the Y component, third is the Z component, and then the last is the actual bval. So as we go further on, you can see that the bval is 1,000. And we can also get the polarity. So when I type in pol, these 3 zeros are just indicating to us that our bvex are sampling the entire sphere. So the next thing we're going to do is take a look at another d-value sequence. So this is subject 2 in our example data set. And this one has multiple b-values. So when I read in the bvex and bvals, and I'm just going to plot that image. So you'll see that we have some bvals in the 1,000 range, some in the 2,000 range, and some in the 3,000. So it's not color coded, so it's a little bit hard to see. But what happens is the higher your b-value, the more diffusion that you allow to happen. So that's what this image is showing here. So your first image is your b0, your second image is your b1000, and your last image is your b3000. And you can see the difference between the b1000 and b3000. You're allowing more diffusion to happen. But it also comes at a cost. So there's more noise. Lastly, I'm going to show you a different type of diffusion imaging called diffusion spectrum imaging. So I'm going to use DiPi to get this data set. So from dipi.data, I'm going to import get fnames. And I'm going to import this data set called Taiwan NTU_DSI. So this might take a bit of time. So next I'm going to read in those bvals and bvex and plot that to see what it looks like. And you can see that the sampling scheme is very different. Instead of being almost shelled like the single shell and multi-shell scans that we saw earlier, this one tries to sample almost the entire Cartesian plane. So these different sampling schemes give you you can use them to do different models of analysis with your diffusion imaging. And I hope that was a good introduction. Now we'll get into dMRIprep, and I'll talk a bit more about how the project is actually structured. So bear with me while I just get to the next slide. So you can find the repository for dMRIprep here. It's under the Maprep's GitHub name under dMRIprep. And I'll mostly focus on how the code is organized for dMRIprep. But if you want to learn more about Python package maintenance and all the other files that are involved, Chris Markowitz has written a good guide on contemporary Python packaging and some of his choices for doing that. And If you read this guide, a lot of the other NIPREP's projects are organized very similarly. So looking at this guide will give you a good understanding of all that. Sorry, it keeps on switching on me. Maybe what I'll do is I'll share the actual window itself. There we go. So here's the dMRIprep project page. So all of the code is held within the dMRIprep folder. And within here, you have a couple different subfolders. So you have your CLI folder, and this contains all of the functions involved in the command line interface and exposing different arguments and options. So if I go back, the config folder houses different configuration files, the most important one being the report spec. So if you look at this, this is a YAML file that interprets how the QC report should be structured. So at the beginning, you have a summary of your data set, your anatomical data, and it shows the segmentation and brain masks. And then in this report, we have a depiction of the field maps, as well as your brain masking. So if you want to add different QC components, you would have to modify this YAML file. Next, we have the data. The data folder has any kind of data involved in the project. So it has our sortation boilerplate, but most importantly, it has all the data that we use for testing. So earlier in Martina's talk today, she talked about unit testing. And that's a really big important of our project. For each kind of function, you have different tests that you could write. And we can use the data in this folder to run those tests. The next thing we have are interfaces. So this is a component of NIPipe that I mentioned earlier. It has all of it. The interfaces folder is the one that's doing all of the work. So it has code that's involved in manipulating the images, creating the QC reports, and dealing with the BVEC and BVAL file here. The next thing you have are actually, I'll show you what one of an example interface looks like. So here's an interface to extract all the B0s from your diffusion image. So like an interface has multiple components. There's an input spec, an output spec, and then your actual main interface that runs the actual function. So I mentioned earlier that interfaces allow you to use different software packages, but they can also be useful for running Python functions. So in this case, this interface is running the extract_b0 function that we have. And there's a lot of validation that goes on with these interfaces. So in the input spec, you define all the inputs that are involved, and the outputs, you define all the outputs. And you go even further. So with each input, you define the kind of type that you're expecting. So for my diffusion image, I know it's going to be a file. For my B0s, I know it's going to be a list telling me the place of all the B0s. And for my output, I'm expecting a file. So there's a lot of validation that goes on in defining these input specs, defining these inputs and outputs, and then linking together all of the different components. Next, we have the utils. And the utils folder contains all the custom functions that we have written for dMRIprep. So I'll go to the images page, and this contains the extract B0 function that you saw earlier that, that interface was running. So if you needed to create any custom functions, we have a one to extract B0s, one to rescale them, and one to create the median image. And finally, we have our workflows folder. So the workflows folder is organized similar to a BIDS dataset. So you have your base workflow. This one is kind of going to be like your main workflow that's linking all of the other smaller workflows together. So it initializes dMRIprep, looks for all of the arguments put into the command line, and executes a workflow for each individual subject. Then within each of the BIDS like naming folders, you have your DWI folder, and this one will execute all of the sub workflows involved in preprocessing your diffusion imaging data. So I'm going to go back to the main page now, and I'll head to the README. So we have a couple different communications or routes of communication for dMRIprep. So if you want some immediate feedback, if you're wanting to contribute and not sure where to go, you can find us on Mattermost. If you are signed up for this brain hack, you might already have a Mattermost account, but you can find us in the dMRIprep channel. The other place where we communicate a lot is in the GitHub issues. So any new feature, any bug, any questions get reported as a GitHub issue. And this is a good place to have discussion. Also, if you want to contribute something new, the best place to do it is, the best thing to do first is to create an issue. So that way people know what you're working on and there's no efforts that are being duplicated. The other important aspect on this page is you can see we have a Circle CI badge. So I'm just going to click this link. And so there are two different kinds of testing. One is unit tests, where you create like a test for each individual function. And the second is continuous integration testing. So this combined tests multiple components at once. So you can think of this if, say you were to buy a new car, unit testing would be similar to seeing if the headlights turn on or off, whereas integration testing would be driving around the block and seeing if anything breaks. So with each pull request that gets made to dMRIprep, it runs a series of jobs. So first it tries to download some data, it builds the documentation, it sees if we can deploy this as a successful Python package and or a Docker container. And most importantly, it runs the workflow from start to finish on two example data sets that we have here. One is DS001771, and the second is THP002. And if you're interested in, if you're really interested in continuous integration testing, we have a .circleci folder with a config file here, and this is kind of showing you how the workflows are built and what each step is executing. So it's written in YAML, but it kind of works as under the command key. You'll see that each step is kind of like a bash command that you would execute. Finally, we have our Zenodo. So Zenodo is a place where you can use to cite different software packages. So with each new release, we update this Zenodo with a new set of contributors. You can also preview the files and download them as a zip. So yeah, and dMRIprep has a very liberal contribution model. So we take contributions for, I mean, because this is kind of an academic endeavor, the order of contributions are done in terms of the amount of code that's being pushed. but contributions can be anything. It can be code, it can be documentation, even raising a big issue that helps the pipeline move forward can count as a contribution. So if you don't have too much coding experience, don't worry. There's still plenty of other ways to get involved. So the next thing that I'll do is I'll go over the GitHub issue that we plan to tackle in this tutorial. And it was written in January, and it was meant to determine the number of shells. So earlier in our Diffusion Mri tutorial, we plotted the BVEX and we showed the B-vals and saw the number of shells for a couple different diffusion data sets. So what this issue is asking for is maybe we can find the number of shells for a given DWIS image and report that back to the user in sort of like maybe the QC page. So let's get started on creating a simple parser for that. I'm going to switch the screen that I share. All right, so one really simple way to do this is using the counter package from collections. I'm just going to make the text a little bit bigger. So from collections, I'm going to import the counter package. It seems like my kernel has stopped, so I'm just going to click on this tab and set it to Python 3. I might need to import my data again. So let me just do that 1 second. So I'm just going to define my data, run the import read bvals and bvex. And then I'm going to import counter. Sorry, actually, I should go to our issue solution. So I'm going to also import the diffusion gradient table from dMRIprep and import our data there. So next, we're going to look at the diffusion gradient table, and we'll look at the bvals. And the next thing is DiPy also has a unique function called unique bvals, and this will allow us to just grab the unique bvals in our image. So from dipy.core.gradients, I'm going to import unique bvals. I'm going to feed in our bvals to that function, and we'll see we have 5 different bvals in this data set. So we have 0, 500, 1,000, 2,000, and 3,000. And the next thing I want to know is how many images correspond to each individual b value. So from collections, I'm going to import counter. And then I'm going to use counter to count the number of images in each b value. So we see that for the B0, we have 8 volumes. For 500, we have 6. For 1,000, we have 15. 2,000, we have 15. And 3,000, we have 60. So this is going to be our solution. Well, I guess what we're going to do now is we're going to find a way to include this in dMRIprep. So I'm going to go to github.com/maprep/dMRIprep. And I'm actually going to go to our contributing guide. So if you went to Oscar's talk on Tuesday, he kind of went over a lot of these items already, but I think he stopped at the making a change. section. So we're gonna start right here. So if we follow these steps, the first one is to comment on an existing issue or open a new issue. So we know that the feature that we're tackling today already exists as an issue, so we don't have to worry about that. The next thing that we're going to do is we're going to fork dMRIprep to my own GitHub user. So I'm going to go back to dMRIprep, and I'm going to click on the fork icon. And when you fork a repository, you kind of create a copy of it into your own account so that you can work on it simultaneously without affecting development and having things clash. So you can see this is my GitHub username, and I forked it from the dMRIpreps org. And the next thing that I'm going to do is I'm going to copy it locally. So I'm going to copy this link. I'm going to switch to a terminal mode, and I'm going to copy it using git clone and then that link that I posted earlier. So it's just downloading now. Now we can change directory into dMRIprep ls, and you'll see that we now have a local copy. So the next step, if we want to create a new or contribute to this code, the next step is to create a new branch. So this is going to, so if I could type in git branch r, it'll show that we're on the master branch right now. And just for convenience, I'm going to create a new one. So I'm going to say git checkout-b. We'll call this branch ENH for enhance. And then we'll say count_shells. So now you can see that I've switched to this new branch. And what I'm going to do next is I'm going to open it up all of this code into a code editor. So in my case, I'm going to use VS Code, but you can use whatever code editor you're comfortable with. So let me just switch to VS Code. And on the left-hand side, you'll see all the files laid out for us. So I'm going to go into dMRIprep, go into Utils, and I'm going to go into vectors. And the vectors file is the one that has our diffusion gradient table class. And this is the file that I'm going to modify in order to add that counting shells option. So at the top here, I'm going to import counter. And I'm going to see if I can figure out a place for where I can put the new function that we're planning on applying. So I think I'm going to put it. I'm going to put it right here, and we're going to define a new property. So if you remember some of the other properties that I mentioned, what it allows you to do is if you run the gradient table class, you can type in gtab.b0mask, and it'll actually call that function. So in this case, I'm going to create a function called def count shells. It's going to take in the gradient table itself. So what I expect this function to do is when I type in gtab.count_shells, it's going to give me the output that I desire. So when we're creating these functions, the first thing that we want to do is add a documentation string. So this is helpful for anybody who's looking at the code later and wants to know what this function is actually doing. So I'm going to type in count number of volumes per B value. The next thing I'm going to do is I want the function to return our counter sorted self._bvals. And that's all there is to it. So now that we've added this property to the diffusion gradient table class, we also need to add it as an output to the diffusion gradient interface. So I'm going to go to the interfaces tab. I'm going to click on vectors, and you can see that here is where we have our check gradient input spec, output spec, and the actual main spec that runs this function. So when I go here, I'm going to define a new output in the output spec. So we're going to call this num_shells, and we're expecting a dictionary object in Python. So I'm going to type in traits.dict. The next thing that we're going to do is actually call that function. So if you see here, this is the place where those properties are getting called. So I'm going to type in self._results number of shells is equal to table. So here we're saving the diffusion gradient table object class as a table. Dot count_shells. So there we have it. I've added in that new feature. But before I push it to GitHub, the next thing that we want to make sure we do is add some tests. So we'll do this by adding in some documentation tests. So you can see here an example of what we already have in dMRIprep. So it's what it's doing is you can see that it's going to datadir and using in an example DWI from our test data. You can see that here. So I'm going to click on the data tab, click on tests, and you can see this TSV, which has our bvec file in the XYZ and our bval file. We have it recorded in two ways. One as a TSV, and we also have it recorded as two separate files. So because of that, we want to test out both ways. One, if we feed it in a TSV, do we get the same result? And if we feed it in as a bvec and bval file, do we get the same result? So now I'm going to go over and add a new test here. So we type in these three kind of arrow signs. This is kind of mimicking the command prompt in terminal. So I'm going to type in check.outputs number of shells. And the next thing I'm going to do is I'm going to type out what we expect this output to be. So I've already gone ahead and counted ahead of time the number of B0s, B2500s, B1200s in this file. So I'm just going to go ahead and type that out. So we expect there to be 12 B0s, 32 B1200s, and 61 B2500s in this sequence. So I'm just going to copy this line to this next place as well. So we're checking it twice. Once if we import a TSV, and once if we import a bvec and bval file. And so what I can do now is, let me just save it. And there's two things that I want to check. So one thing that I want to check is the code format. Python has this thing called PEP8. It's a series of guidelines on how you should format your code and make sure everything is formatted correctly. So I'm just going to import my Python in virtual environment. And over here, I already have some packages installed to check for the PEP8 of our files. So I'm going to use Flake8 in this example. So I'm going to call it on both the interface, the vectors file that we just added, and I'm going to call it on the utils. And you'll see that we don't get any output, so that means we're good to go. There's no errors there. The next thing I'm going to do is I'm going to use the PyTest package. So there are a couple of different Python packages that you can use to run these tests. PyTest is one of them. So I'm going to use PyTest to see if these documentation tests that we've added work well enough. So I'm going to use PyTest dMRIprep /interfaces /vectors. And oh, it says that we don't have NumPy installed. So maybe I'm going to pip install actually dMRIprep in this environment so that all the packages that we need for running these tests are available. So this is just going to take a bit of time. Let me actually stop this. I'll switch to like another virtual environment where I already have these packages installed. So I'm going to do PyTest dMRIprep /interfaces /vectors. And you'll see that it's running the tests now. Let me actually make this a little bit bigger. And you'll see that it failed one of the tests. So it looks like for the TSV, we wrote that it expects this line, but we actually got this line when we ran the test. Sorry, I'm gonna go back. So let's just fix that really quick. So I guess it's just expecting a floating point instead of a whole integer. I'm just going to clear this and let's try running the test again. And so yeah, our tests passed. So now we're good to go. So I talked about as like a next step to this workflow, what you can do is integrate this output into the QC page, but that's kind of like a more advanced workflow. We'll end off right here. I'll show you how to add your changes and push them as a pull request to GitHub. So I'm going to type in git status. And you'll see that we have two files that show up as modified. I'm going to stage them right now. So I'm going to type in git add and then dMRIprep /interfaces /vectors. And I'm also going to type in git add dMRIprep /utils /vectors. And before I add it, I'm just going to add a commit message. So this is going to show up in GitHub as like an explanation for what happened, what was done to these two files. So I'm going to type in add shell counting. And the next thing that I'm going to do is I'm going to push my changes using git push. So one thing that is shown here is on my GitHub page, we don't have this branch enhance count shells. So GitHub doesn't know where to exactly push it. So what we're going to do is copy this code. So we're going to do git push set an upstream to origin, which is my branch. And I'm going to push it to a count underscore shells. So the other thing that I forgot to mention is that I guess before even creating a new branch, the next thing you want to do, the one thing that you want to do is set a remote. So I'm going to say git remote add, we'll call this remote upstream. So my repository is going to be the origin, and upstream is going to be the actual main repository. So github.com/mypreps/dMRIprep. And what you can do is you can do a git fetch upstream. So this is going to fetch all of the different branches on our main repository. So now if I type git branch r, you'll see that we have a mix of branches from my repository, so the origin, and the main dMRIprep repository upstream. So now I'm going to go back to my GitHub page. You'll see that our push was successful, and you have a link that shows up comparing pull request. So I'm going to click on this. And so I mentioned that there was a feature that I was hoping to get to, but I didn't get to it. It was actually adding the shell count to the QC report. So to make this pull request, I'm going to call it a WIP, or a work in progress. And I'm going to type in adds number of volumes per p-value to QC report. And I'm going to create it as a draft pull request. So what a draft pull request does is it prevents the maintainers of the project from accidentally merging in the code until you've said that it's okay to release. The other thing that we can do, so you'll see that already all of our workflows from Circle CI are running on this on these editions. So it's going to check, it's going to run the workflow end to end on 2 different data sets and see if our code breaks anything. So when we go into Circle CI, actually, I'm going to go into one of the older pull requests that was already run. And I'm going to go into one of the runs just to show you what that looks like. So here is an older pull request where we ran the code on the THP002 dataset. If I click on artifacts and I open this HTML page, so this artifacts are basically all of the outputs that you expect the pipeline to give you at the end when it's done. So I can look at this QC page. I can, take a look and see if it looks okay to me. So this is another quick check that we do before merging any code, just to make sure that the QC page looks okay and any changes that are encountered don't affect the visualization. So that's the end of my talk. Thank you all for joining in, and I hope you learned a lot about some of the NIPREP's tools, dMRIprep in particular. But if you want to get involved, feel free to look on the NIPREP's page. You can see that there's a project board with the roadmap, the development roadmap for fMRIprep, dMRIprep, and all of the other projects in one go. So you can take here if there are any, look here if there are any issues that you'd be interested in tackling and claim them.